Welcome back to this lecture on thermohaline circulation. This is the module number 2, and this is a part of the NRC in marine sciences. In the first part, I have briefly described the main structure of the thermohaline circulation and listed that there are 4 components of the thermohaline circulation, which are sinking, spreading, upwelling and return flow. Now let us look at the sinking process in little more detail in this lecture. The wind-driven circulation, as I mentioned in the first lecture, is confined to the upper 1 kilometer of the ocean. In contrast, the deep convection that occurs in selected regions of the ocean can penetrate into the deepest regions of the ocean. That's one major difference between the wind-driven and wind-driven circulation and the circulation caused by deep convection. Wind-driven circulation is confined to 1 kilometer, whereas the deep convection can reach into much deeper depths into the ocean. Such water that reaches into the deepest part of the ocean creates a density gradient, and such density gradient can drive the flow in the deep ocean. That is a part of the thermohaline circulation. Thus, the deep convection and sinking is a very important component of the thermohaline circulation. Now, this deep convection occurs only in very few selected regions of the ocean, as I mentioned in the part number 1. The condition that is required for the water parcel to sink is that the water parcel should attain density which is higher compared to the density of its surrounding waters. So, the two conditions have to be satisfied. One is that there should be a loss of buoyancy, and the second condition is that the parcel should be able to penetrate the barrier of stratification and sink to deep depths. So, let us look at those processes. The first condition for the sinking of water parcel is a loss of buoyancy. The buoyancy is defined by this expression here, B equals minus G rho P minus rho E upon rho P. G is acceleration due to gravity in meter per centimeter square. Rho E is the density of the surrounding water or the ocean in general, and rho P is the density of parcel that we are looking at. If a water parcel attains a density rho P which is higher than the density of the surrounding water, the parcel would sink. In this formula, there would be negative buoyancy. If rho P is greater than rho E, the term B would be negative. A water parcel would become negatively buoyant and sink to deep depth of the ocean. So, B gives a measure of the buoyancy of a water parcel. How does the buoyancy of a water parcel at the ocean surface can change? It can change either by loss or gain of temperature or by addition or removal of fresh water. That is called as air-sea buoyancy flux, given by this formula capital B equals G by rho naught alpha by Cp Qn plus rho naught beta S E minus P. G again is acceleration due to gravity, and rho naught is the density. Alpha is coefficient of thermal expansion of seawater, and beta is coefficient of saline contraction of seawater. Qn is the net air-sea flux. This net air-sea flux is a sum of the effects of radiation, loss by latent heat flux, sensible heat flux, and outgoing long-wave radiation from the sea surface. The second term has rho naught beta S E minus P. S is the salinity, E is the loss of water by evaporation, and P is the gain of water by rainfall. The net effect of heat flux and freshwater flux decides whether the density of a parcel of water can increase or decrease. So, for sinking to happen, there should be loss of heat which would make a water parcel dense. And this process in fact happens in higher latitudes. This figure shows you a global distribution of buoyancy flux. The units here for convenience are watts per square meters. The regions where the shading is in yellow and red shows where the water is buoyant. Wherever the shading is blue and green, there is negative buoyancy and the water parcel is heavier compared to its surroundings. Now, if you look at this figure, it's difficult to identify regions that can cause sinking into the deep ocean, because this figure takes care only of heat and freshwater fluxes by evaporation and precipitation. In higher latitudes, there are other processes happening. For example, there is ice formation. When there is ice formation, the brine is rejected into the surrounding water. This is addition of salt into the surrounding water. This addition of salt into the surrounding water increases its density. In short, when there is cooling, there is ice formation taking place and there is rejection of salt, and this can cause an increase in density of the water parcel. This in fact is an important process which promotes active sinking in the regions of sinking. One more condition has to be satisfied for sinking to happen. The water parcel should be able to penetrate the stratification of the upper ocean so that it can reach into the deeper waters. A measure of the stratification of the seawater is given by the parameter known as Brun-Weishaler frequency or stability frequency. Stability frequency is written as n square, which is g by rho d rho by dz. D rho by dz gives you a measure of the vertical gradient in density. This figure compares the stability of ocean water at two latitudes. One of them is tropical, which is shown in red, and other is high latitude, which is shown in green. The green curve in this figure corresponds to this high latitude location, and the red curve corresponds to a tropical location. This is plotted for a depth of the top 1500 meters of the water column. This figure shows that in the tropical region, there is a region where the water is highly stable, or in other words, in this region, the water is strongly stratified. A parcel which descends or sinks from the surface has to overcome this stratification barrier so that it can sink deep into the ocean, which means that it has to attain a density which is sufficiently large so that it can sink beyond these barriers. When you look at higher latitude, such layer of strong stratification doesn't exist in high latitudes. Therefore, it is easier for the water parcel to sink into the deep ocean. Thus, two conditions have to be maintained for sinking into deeper waters. One is large buoyancy loss, and the second is that the water column should be sufficiently weakly stratified. The process of deep convection and sinking happens in 4 phases. The first phase is called as preconditioning. The second is convection and mixing. The third and fourth are sinking and spreading. The water column has to be preconditioned at first. The preconditioning happens by Ekman suction. Ekman suction is caused by a positive wind stress curl. A positive wind stress curl lifts the pycnocline in the ocean upward. When Ekman section happens, the weakly stratified water, such as in the middle of this picture, is lifted and it is exposed to the surface. After the preconditioning happens, in regions of positive wind stress curl, the water near the surface is weakly stratified. The next process is heat loss to the atmosphere. The water here is ready to be cooled and attain density higher than its surroundings and to sink into the deep ocean. Thus, in phase 2, there is intense heat loss happening and the parcel becomes heavier and begins to sink. In the mature phase of sinking, there is widespread sinking happening in the region. The entire water column is uniformly mixed. The mixed layer becomes very deep and the water near the surface can now sink up to deep depths. The fourth phase is spreading, and in the spreading phase, even though the surface processes of sinking has stopped, the water in the deep ocean is heavier compared to the surroundings and then it starts spreading. These are the four phases of deep convection and sinking. Such deep convection and sinking are restricted to few regions, as I mentioned, and one of them is in the higher latitudes of northern Atlantic and then near the continental shelves of Antarctica in Weddell Sea and Ross Sea. A picture of the oxygen distribution in the vertical in the ocean gives you an idea of sinking of water masses. Now, the water at the surface in the ocean exchanges oxygen with the atmosphere, and usually the surface waters are high in oxygen content, as you see in such regions. Once the water sinks into the deep ocean, the oxygen is consumed and the concentration of the oxygen decreases. Therefore, as water ages, its oxygen content decreases. This figure shows you a vertical section of oxygen from the northern Atlantic to the southern part of Atlantic close to the coast of Antarctica. So this is the northern Atlantic and here is Antarctica. The surface water in the northern Atlantic is rich in oxygen, and if you look at this picture from north to south, you can see that the concentration of oxygen is decreasing from north to south. The water, as you go progressively towards south, the concentration of oxygen in the water is less and less. This is an evidence of water with high oxygen concentration at the surface is sinking to depths of about 2000 to 3000 meters and spreading all the way to the southern hemisphere. If you compare a similar picture with the Pacific, this is what you would see. The scale is such that the purple shows very low oxygen and the red shows high oxygen. Let us look back at this picture where the northern Atlantic has high oxygen at a depth of about 2000 to 4000 meters. In contrast, if you look at the Pacific, the water in these depths are very low in oxygen. The high oxygen waters in the Pacific are seen near the Antarctic region, where there is surface water sinking to intermediate depths. This is a clear evidence that there is no sinking happening in the northern Pacific Ocean. But there is sinking happening in the southern Pacific Ocean off the coast of Antarctica, where one can see waters with relatively higher concentration of oxygen. From these figures, it is very clear that there is sinking happening in the northern Atlantic, but now sinking happening in the northern Pacific. The third component of the thermohaline circulation is spreading, and we will look at the spreading in the next part. Thank you.